Oh, week was good. Relaxed. It's my first week after exam, so trying to have a social life after 12-hour study days. All right. Yeah, I think you're all quite busy with your first exams, right? The chem. Have you finished that already? How was it?
It was a lot different to what we were expecting, but it wasn't too bad.
Okay.
A lot more science skills than content. Theoretical. Yeah. There's no calculation questions. So the test was based on 4 dot points on the 1 to 5 and 6, but none of them included calculations. Solubility and then the acid-based theory.
Okay, we'll get started. So we are going to be touching upon acid-base theories now. Okay, so the first thing I'll get all of us to do for this module, what's the first thing that I expect when you look at a module? Yes, why do we go to the content focus, Mania? Why is the content focus important?
Because it gives us sort of like a skin of everything we need to understand the logic.
Yeah, and all the high yield stuff, right, in your exams is in the content focus. Literally a little sneak peek into what your 2022 HSC Chem exam is going to be about, okay? So, first thing we're going to have a look at is this content focus, and what I'm going to do is, I've already bolded the keywords for you, but a couple of seconds, we're going to start asking people each of these keywords. So, we're going to start with you two with definitions of acid and base soon, and we're going to move on and ask industrial context, what we currently understand. Okay? Good. Luca, what do you understand about acids and bases so far? Give it a go. Have you got up to this at school? Acids and bases? Yes, no, I can't hear you.
Hello.
Yeah, I can hear you now.
Hello.
Yeah, so what have you gone through?
Hello.
Okay, I'll mute you for now, so we could just mute yourself, and then when I ask you questions, just unmute yourself, okay? Good. All right, so Pranav, definition of an acid. What kind of solution? Good. So the definition of an acid that you should know so far is it releases hydrogen ions in aqueous solution. Everything else is characteristics. The word sour should not be in the definition. It should be a characteristic, right? It's like saying, if you were to describe a human, how would we describe a human? Yeah, you could say they're bipedal apes, multicellular eukaryotes, heterotrophic, but you wouldn't say something like some humans like sour candy. It doesn't describe what a human is, right? Good. So an acid is a substance that releases hydrogen ions in aqueous solution or in water, okay? And a base, Anj, how would you define a base?
It either accepts protons or releases hydroxide ions.
Good. We haven't got to the proton story yet, but very good. So a base releases hydroxide ions in aqueous solution. So Anj, whose definition are we talking about right now? Good. When did he propose this? 1880. You don't need to know the dates, but it's an interesting concept, this one. Good. So that's the definition of an acid base you should have known coming into chemistry so far. We're going to convert that to an updated definition shortly. That's what we need to understand so far. Now, acids react in particular ways. What kind of reactions do our acids have? Yeah, so one of the main reactions that an acid has is an acid-base reaction. What does an acid-base reaction give you, Father? And if it was a carbonate, what would it give you? Hydrogen gas? Yeah, right. Salt, water. When do you get hydrogen gas, Father? Acid metal reactions. Those are toxic. You need to think about this. You drop acid on a metal, you produce a toxic gas. Hydrogen gas is used in chemical warfare, right? It's nasty, right? Carbon dioxide is harmless. We have it in our air right now, okay? Good. What are some other acid reactions that we can have? So I've kind of given you the other one, which is acid and metal. That's low yield. Acid metal gives you salt and Hydrogen gas. Very good. Now let's talk about uses of acids. What about in everyday life? What do we use acids and bases in? Okay. How so in food?
So lemon with alcohol.
Okay, so what acid does lemon have? Yeah, there's citric acid. There's a ascorbic acid because lemon is rich in vitamin C, which is ascorbic acid. But there's many acids, so we'll say food, additives. What else? Not just acids, what are bases? Do a little experiment, like give you a little understanding. Bacteria, they eat food particles in our mouth and produce acid. So what would neutralize that? Saliva is slightly basic. Toothpaste. Toothpaste is all alkaline to neutralize acid content from decayed food. Does that make sense? So in everyday use of bases, so acids is food additives, bases is, for example, toothpaste. Any other use cases of acids and bases? Everyday use? Yes, that's food additives again. What about heartburn? Does anyone know what heartburn is? Does it have anything to do with the heart? Heartburn is called heartburn because it feels like your heart is burning. But what it actually is it's your esophagus getting irritated from gastric acid from the stomach coming back up. So it's reflux disease. We call it gastroesophageal reflux. Is it bad for you? It is bad because what happens when you irritate and stress cells in the human body, they start to mutate and they can become cancerous. So it is a risk factor for esophageal carcinoma. Okay, so that's a bit of a medical point. But coming back to this, it's also used we use bases. Specifically, we use bases such as, I can give you various examples. Calcium oxide is one of the compounds in antacid. An antacid is a tablet you take to mitigate reflux disease. So the base in that tablet will neutralize some of the stomach acid, minimize the amount that comes back up the esophagus. Okay? We're going to come back to all of this again. What about industrial uses? What are some industrial uses of acids and bases? This is the important stuff because you need to know why you're sitting here learning this stuff right now, right? Why are you learning about lemons and toothpaste? It's not important. I don't care about toothpaste. What's industrial use? Who's of South Asian ethnicity? Well, guess what? All of you put your hands up at risk of heart disease, right? All of you have a higher risk of getting diabetes, atherosclerosis, me included, plaques in your arteries, which can cause heart attack. And what is a medication that every single person with heart disease or risk factors is put on? Not Panadol. Very close. It's actually very close. Another pain reliever. That's the same thing. It's a fancy name. Anyone heard of aspirin before? Helston loves aspirin. They teach you aspirin as your industrial reaction. The crack experiment last year was on aspirin synthesis. So for industrial reactions, one of the key use cases is the synthesis of aspirin. Aspirin's formal name is acetyl salicylic acid. It's an acid, right? And we need to make sure the dosage is perfect because we're giving it as medicine, right? Does anyone know how we calculate concentration very accurately for acids and bases? It's a fancy name.
Titration.
Yeah, so you learn about titration this year, this module as well, right? So we titrate acetylsalicylic acid to make aspirin in medicine. And that's used to save lives because it thins the blood as well, okay? So that's used for heart disease. Any other use cases? Any other industrial uses of acids? It's one very important one. Who's eaten rice in the last week? Right? Now, how big is the global population? 7 point, is it 8 now? It was 6 when I last checked. So you can see how exponentially it's growing, right? Because the more people there are, the more babies each person makes, it keeps going up. We're using 3.5 planets worth of resources right now. It's not sustainable, right? At this rate, we will deplete all of our food resources, etc. So what happened in World War II was there was a huge food shortage, all right? There was a lack of fertilizer to provide and produce the crops in the rice. Now, what reaction did you learn in Mod 5? Yeah, the Haber process was used to produce what substance? Ammonia. Nitrogen combines, I'm not going to balance this, but you know, nitrogen combines with hydrogen to form ammonia gas. Ammonia is not a fertilizer. What needs to happen next is it must be combined with sulfuric acid to form, what do we form then? Good, ammonium sulfate. Again, you can balance this yourself. But point being, this is your fertilizer. Ammonium sulfate is a salt that provides the nitrogen in the soil for plants to grow, right? And this fertilizer enabled us to produce more crops and feed the global population. It's one of the reasons why we're alive today. We wouldn't be if we hadn't discovered how to make this type of synthetic fertilizer. Before this, we used to use bird poop, right? That was our most abundant source of fertilizer, and that's hard to get, right? But this was a huge game changer. Does anyone know who discovered the Haber process? Fritz Haber was a war scientist in Germany, so he actually wanted to kill people. He wanted to create like the gas that they used in the gas chambers, and kind of backfired, and now he's helped our global population. Yeah. Good. Anyway, coming back to this, what about degree of acidity? What is that dependent on in terms of chemistry? Rabab, what would you think? Is it to do with concentration, strength of the acid? What do you think? Good. Okay. Does strength have anything to do with concentration, everyone? Or not? Do you want to elaborate? What is strength and concentration? What is the difference?
So like strength usually talks about like how the hydrogen ions or like ionize in the solution. It's the degree of ionization.
Good.
And then how much particles there is in those.
That's it. Right? So concentration is just how many moles of something is there in a liter. Right? Doesn't matter if it's a weak acid, strong acid. We could have 10 moles of vinegar in a bucket of water in a liter, and we'd say that's a concentrated solution of vinegar, right? But vinegar is always a weak acid. It never goes to completion. So if we were to write the reaction for vinegar, it would always form what we call an equilibrium because it's a weak acid. Not all of the HA releases H plus ions, right? There might be a large number of HA molecules in this jug of solution, but not all of them actually break up to form H plus. And that's what makes it a weak acid. So we're going to come back to this again, but remember, strength and concentration are two completely unrelated concepts. Does that make sense? They're independent to one another. You can't say it's strong because it's concentrated. That's completely wrong. Okay? Concentrated, in a nutshell, is just how many molecules are there in a volume, moles per liter. Strength is all about equilibrium. If there is an equilibrium, it's weak because not all of it has formed H plus ions. If it goes to completion, we say it is a strong acid. So we'll come back to that, okay? Good, so that's the breakdown of the content focus. Very good. So we're going to skip the key verb. Let's come here to the inquiry question. Now we've already described and defined what an acid is, right? An acid and a base is to do with hydrogen and hydroxide ions. Now what was the limitation with that theory, Father? What was the end that we had for the definition of an acid and a base? In? Good. Can acid-base reactions happen in non-aqueous solutions? Can. It definitely can. And so immediately, do you all see the limitation of your theory? We can't describe an acid or base outside of water, but acid-base reactions happen outside of water. So we're going to fix and resolve that theory soon, okay? Good. Let's start with this. What does this stand for? Yeah, right. You need to realize communication is very important. If every time I had to say the word for human, I had to say bipedal sentient ape with language capacity, how tedious and non-succinct would communication be? So in chemistry, it's important. If I say word, I can, expand all of that meaning just from that one word, just like how you can. And that's what IUPAC is here for. IUPAC is the International Union of Pure and Applied Chemistry. They're like the governing body on how to name things. When you do organic chemistry, which is going to be in Mod 7, you'll learn they'll literally dictate the entire syllabus. So I'll show you how to name every single type of organic molecule. Okay? Good. So we're looking at inorganic acids. Do you see that? So we're not going to be looking at the vinegar, which is an organic acid. We're going to be looking at the basic acids. Now, before we name them, let's talk about some other properties. So Pranav said they're sour. What are some other properties of acids? Just go across River. That's all right. I'll come back to you, Tanisha. Good. What does pH stand for? What does pH stand for?
Oh,
Why would they call it pH? It was concentration. You're right, but what does pH stand for? Very close. Technically, right? Power of hydrogen. pH stands for the power of hydrogen. It's an old concept, but it's hung on, right? It's to do with hydrogen ion concentration. So very good. pH is less than 7. I'll just give you a little tip though. pH changes with temperature. So it's at 25 degrees specifically that pH is less than 7. pH of water, in fact, is perfectly 7 at 25 degrees, but it changes, and we'll talk about that soon. It can cause burns. That's another point. What about litmus paper? What do we know about litmus? Yeah, very good. So when I think of acid, I think red. I think base, I think blue, right? It's just colors. They don't have colors. They're all clear. But in my head, that's what I imagine when I think of an acid versus a base. So an acid will turn blue litmus paper red. Okay? Litmus paper is just a natural indicator you can get from tree bark. So that's how they create litmus paper. And you can dip it in solutions and change its color. Okay? Good. So blue litmus turns red, and then the formal definition is present here. Now, if they release ions in solution, are they conductive or non-conductive? Yeah, they have to be conductive in that scenario. Okay, so those are the properties of acids. We've spoken about their uses. One use I haven't mentioned, maybe good to just know off the top of your head, is lead acid batteries, right? Now, who remembers galvanic cells? Vaguely, right? What's the general gist of a galvanic cell? We're complicating it. The key gist is we enable a redox reaction to occur where there's a transfer of electrons. But what we force is we force the electrons to travel through an external wire, hence producing electricity. So a galvanic cell is manipulating a redox reaction to create electricity. So it's converting chemical energy into electrical energy, right? Your batteries do the same thing, right? So when you are just turning the car engine on, all that electricity is produced from chemical energy in the lead acid battery. However, when you drive, you force a reverse reaction to happen, and you can store some of the electricity as chemical energy. That's why those batteries in your car last tens of years. You only have to replace them every 2 decades or so. Okay? Good. Now, what about bases? Again, I'm not going to say anything. Let's quickly go across. This is the easy stuff. So Maya, tell me 2 properties of bases.
pH of more than 7.
Yep. One more.
Tastes better.
Good. 2 more. Right, litmus paper. Blue, right? Because we said bases are blue. So it turns a red litmus paper, blue. Very good. Conducts or non-conductive? Conductive. Think about it. It releases hydroxide ions in aqueous solution, so it must be conductive. Anything that releases ions, when you apply it under electrical field, the ions travel in a uniform direction. That's what electricity is. Any moving charge is electricity, right? Good. Bitter or sour above? Bases. Very good. So that's how, if you really want to know, you can taste it and you'll find out. Good. Let's move on. Uses. Here you've got some uses. I think the key ones to remember. Detergents is good. So bleach is intrinsically basic, right? And that's how it can kill bacteria. It can change the pH so significantly that enzymes denature in the pathogen, etc. Cooking, we'll talk about that. And then we've mentioned that it can be used to treat acid reflux. I think this would be one of the most important everyday uses that I would go to if I were to mention it. Very good. All right. Now, we're not going to talk much about organic acids because, like I told you, it's not in the syllabus just yet, but you're going to have to learn it eventually. And chemistry is not like different books. It's not mod 5, 6, 7, 8. You're learning it in modules to understand the big picture. So link it all together. The one thing I will say is for organic acids, they all have this functional group here. Pay attention to this. See this carbon? It's going to have a double bonded oxygen, and it's going to have an OH group. And it's this OH that can drop off in solution and form hydrogen ions. And that's what makes organic acids acidic. Does that make sense? You would also see this written as CO for this oxygen, O for this oxygen, Has anyone seen that before? COOH? You might have seen CH3COOH. You might be wondering, why did they write it that way? The reason they wrote it that way is there's a carbon connected here that has 3 hydrogens, and there'll be a COOH next to show you the actual structure. So here is the exact compound. What are you looking at? What's staring you right in the face right now? Vinegar. That is the chemical formula of vinegar. Vinegar is formally known as ethanoic acid, and you'll learn how to name it in Mod 7. Okay? But how do you know it's an organic acid? Yeah, we call this the carboxylic acid functional group, or the COOH functional group. Does that make sense? Very good. Good. Look, any questions so far?
No, I'm all good, thank you.
All right, good. If you have any questions, just jump in, butt right in, ask me anything at all, okay?
Okay, thank you.
Good. All right. So continuing on, that's it for your organic acids. Not too difficult. Any questions so far? Pretty easy thus far. Very good. Here you see a more complicated acid. This is 2-hydroxy 1,2,3-tricarboxylic acid, or in simple terms, this is what we call citric acid. How do you know it's an organic acid, Maya? What do you see? Only 2? 3, right? So citric acid has a, if I asked you, how many hydrogen ions would this molecule release in solution, what would you say? 3. Remember, it's only this hydrogen that comes off. Not this, only the hydrogen at the end of that COH. Okay, very good. All right, let's talk about inorganic acids. Now, with inorganic acids, there are 2 categories. So when you think acid now, you need to think, is it a binary acid or is it a polyatomic acid? Now, I want you to remember this. All these rules eventually should go out of your head, in the sense that when you start naming acids enough, you don't have to go, what was rule number 1, what was rule number 2? Okay, it should be intuitive to you. To start off, we'll go through these rules. I don't even memorize those, because after you've seen acids enough, you just look at it and you know what it's called. Okay? But to help you all out, when you're naming a binary acid, the way you know it's a binary acid is it'll be hydrogen connected to one other element. See how there's 2 elements here? Binary. The other element is usually a halogen. So, Thava, pick a halogen. Group 7. Pardon? Fluoride? Okay. Hydrofluoric acid. Right? Pick another halogen. Iodine. So hydroiodic acid. Pick another halogen. You shouldn't have to look. Yeah. Big bromine. Hydrobromic acid. Pick another halogen. I don't think sulfur is a halogen. I think sulfur has a 2-. Pick another halogen. Chlorine is the most important one I was waiting for, right? So it forms hydrochloric acid. What's the pattern you're picking up? The beginning is always hydro, and it always ends in ic acid. And you just add whatever halogen is present. It's chloric if it's chlorine, it's bromic if it's bromine, it's iodic if it's iodine. You'll see that pattern there. So whenever it's a binary acid, you always start off with hydro, and you change the "ide" to ic acid. Right? So if we're talking about a chloride ion, what does it become? Chloric acid. Now again, what did I tell you? Eventually it should not be in your head. You should just look at the acid and know what it's called. So this is where practice makes you perfect. Okay? We're going to move on for now. I'll pick on you as we go through more acids. Now with polyatomic ions, I wouldn't say it's more complicated. You just need to know your polyatomic ions. So let's start with this. I'm going to give you different valencies, and you're going to tell me what polyatomic ions fit these valencies. These are your headings. Now, there's only one polyatomic ion that has a +1 valency. Fava, what is that? You should remember it from last lesson. Pardon? Carbonate. What was the one rule of the solubility table you cannot forget? You need to revise. Yes, and? group 1 metals are all soluble. That is the universal rule of the solubility table. All group 1 metals and ammonium, always soluble. You can't forget that, okay? So ammonium is the only polyatomic ion with a +1 charge because it's like a group 1 metal. Does that make sense to everyone? Good. So that's the positive 1 charge. What about negative 1? Do we know any polyatomic ions with negative 1 charge? What about? Very good. Nitrate's 1, NO3 minus. Give me another one, Mahi. Acetate, right? So that is not a polyatomic ion. I will reinforce this to you. It can break apart, but you could call it a polyatomic ion. The reason I'm saying it's kind of not is because what is a polyatomic ion? It's an ion that pretty much acts like an element. It acts like a unit. You can't break it up into smaller pieces. However, you can break this into smaller pieces. But we'll add it there, acetate. What about 2 minus? Pranav? Good. Sulfate's 1. But we're missing one more. What about this ion here? What do we call that? Nitrite. How did we know that NO3 was nitrate, NO2 was nitrite? Yeah, I remember this. 8 always has 1 more than 8. Meaning that it's already 8 another atom, something like that, right? But 8 has 1 more than its 8 counterpart. And this is going to be important because when we go through sulfate, there must be a... Yeah, so this is your sulfate. So there must be a SO3 2 minus. Rabab, what would you call that? It hasn't eaten yet, so it's... Yeah, sulfite. Very good. What else do we have for negative 2? Further, now you can talk about the ion you mentioned earlier. And there is one ion you should know that has a 3 minus. What is that? Good. So that is your list of polyatomic ions you can't forget. You've got to know this. This is part of year 11 that's essential to your progression. Now, the reason I brought this up is your polyatomic acids are named based off these names here. We'll go through that now. Okay? Have a look at this. If the polyatomic ion ends in 8, what does it become? Ic acid. Okay, so remember, 8 becomes ic acid. If the polyatomic ion is an ite, what does it become? An us acid, right? So let's go through this. If it was SO4 2 minus, that's sulfate, what acid would it become if it was bound to hydrogen? Yeah, so you go sulfur, instead of writing the 8, you go to ic acid. You guys see that? So now what I'm going to do is going to pick random people and ask you what you'd call these acids. Are you ready? Okay, Atharva, what would you call this? Hydrogen iodic acid? Hydroiodic. Remember, it's hydro. This is iodide, and you convert the iode into ic acid. So this is hydroiodic acid. Okay, very good. So what your head should be doing right now, you should be thinking, okay, is it a binary? Is it a polyatomic? And if it's a binary, you name it hydroic acid. If it's polyatomic, you apply these 2 rules. Does that make sense? So, Mahi, your turn. What would you call this acid? Very good. So he thought, okay, is it binary or polyatomic? What is it? Good. So now he applied these 2 rules. What ion is this? This NO3 minus is nitrate. What do we do to the 8? We convert it to ic. So it just becomes nitric acid. Very good. What about Nisha? That one, I'll give you this one. Binary or polyatomic? Good. Very good. Rabab, back to you. What about? Good. Nailed it, right? It's a polyatomic ion. So we go, okay, well, what's the ion? It's carbonate. So you convert that to ic acid. 8 becomes ic. Good. Atharva? Close. Phosphoric acid. This is where you just have to see the acids, and when you see it enough, you just clicks. Okay, so this is where practice will really help you, and you'll improve so much more with that. So now, for the rest of this module, every time you see an acid name it in your head, so you're comfortable with this. Okay, and you'll get much better over time. Good. We'll move on for now. I know it seems like we've rushed this part. That's because you can easily pick this and improve throughout the entire module. We're going to go to the high yield stuff now. This is the big flow chart which I wanted you to build in your head. Is it binary? Is it polyatomic? It's binary hydroic acid. If it's polyatomic, an 8 becomes ic acid, and it becomes. Yeah, so if I forgot to give you one of those, but if I gave you this, what would you call this? Sulfurous acid. Good. And finally, one more, Pranav. What would you call this? Very good. Nitrous acid. Good. So we pretty much named every acid you need to know. Pretty much it. Not too hard. Good job. All right, let's move on. You can do all this other name in your own time. And this as well in your own time. So again, I guess homework for this lesson would be at least up to page 9. Maybe just circle that as your where I expect you to be up to. You can do it in your books if you don't have the booklets yet. But let's move on. Okay. Prithvi, can you read this dot point out for us? Yeah, such a wordy dot point. Trying to get to the point. So, what is it telling me? Let's say if I have a short attention span, Arch, can you dumb it down for me? What is it saying? Very good. That's what they should have written here, right? How do we use indicators to understand acids and bases? Very good. So we'll start with this. What is an indicator? Okay. Yes, but you're not thinking about the indicator I'm thinking about. I'm thinking about the thing you drop into a solution that is good. So how would you describe that to me? If I was not a blind person, if I've never seen an indicator before, how would you describe what it does? Based on? The percentage starts to complicate it. I just say based on concentration of hydrogen, or based on acidity, right? So it changes color based on acidity. Everyone with me? Now, to understand how it does that, you need to understand what an indicator actually is. This is a rule of thumb. This is not a whole exceptional rule, but majority of your indicators themselves are weak acids. Again, not every single indicator is, but for the purposes of the HSC, think of pretty much all indicators as forming a weak acid. Now, what did I tell you all about weak acids and strong acids? What does that have to do with degree of ionization? Does it ionize to 100%? Or is there a reverse reaction and doesn't ionize to 100%? Now, Luca, you see a double arrow here. Does that tell you, is this acid ionized to 100% or less than 100%?
Less than 100%.
Very good. Goes less than 100%. So we call this a weak acid. Do you all understand that? If you ever see a single directional arrow, it's 100% ionization. If you see double arrow, what is it? It's a weak, yeah, it's less than 100%, it's a weak acid. Very good. Now, the second you see a double arrow, you should still remember mod 5. Whose principle must we obey? The shadowless principle. Very good. Now, that's the first principle of an indicator. An indicator itself is a weak acid. The second principle of indicators is that the bound and unbound form of the indicator have 2 different colors. So when hydrogen is bound to the indicator, there is one specific color. When hydrogen is not bound to the indicator, there will be another specific color. Now imagine this, everyone. Imagine that you got this very indicator that goes blue when it's in its H-in state, and it goes, let's not do orange, let's do another color that has a good mix. You make purple from blue and yellow, right? Or is that, no, that's orange, that's red. Is it blue and red? Okay, blue and red, all right. That makes purple. So we'll say this is color 2. Okay. So this is your indicator that you see. Okay. Now let's say that you added in a solution of acid. I want you to tell me which direction will this equilibrium shift according to Le Chatelier's principle. So we've added the indicator to acid. So again, I want a final answer. Think in your head, and I want you to give me a final answer. What direction will this equilibrium go, and why? And for Bob, when you're ready, I want you to give this a go. Take your time, no rush. Yeah, so when you add this indicator into a solution of acid, what color will the indicator become? And Luca, I want you to think about this too. I'll ask you as well what color after. I want you to see. There we go.
Bluish.
Okay. Why do you say that, Rabab? We'll start with this. Rabab, what are the 3 questions you always ask yourself when answering Le Chatelier's? Yeah, SOD. What's a stimulus? What is the exact opposite of that, which is what Le Chatelier's principle is trying to induce or produce? And D is what direction do we go to achieve that opposite, right? So what would the stimulus be, Mahir, when we add this to a solution with acid? So when this indicator gets added into this acid solution, what is a stimulus? What are the 3 types of stimuli we can have? We're deviating from the key things I taught you. Pressure, volume. Is color one of them, Mahir? No. So again, I'll ask you one more time. What is a stimulus here? Very good. We've changed the concentration of something in this equilibrium. What have we changed the concentration of? Hydrogen ions. Didn't you all tell me acids release hydrogen ions in aqueous solution? So there's already hydrogen ions floating around in the solution. So the stimulus is an increase in the concentration of hydrogen ions. Do you all agree there's hydrogen ions right here? What is the opposite of that? Yeah, we want to decrease the concentration of hydrogen ions because we've disrupted the equilibrium. We've changed this ions concentration. So about which direction would we go now to decrease the concentration of hydrogen? Yeah, and you're completely right. It goes more blue. Does that make sense? Any questions so far? Luca, does that make sense? Any questions at all?
Yeah, it makes sense, thanks.
Okay, very good. So yeah, so the key just here is you all see how the indicator is now going to go from a purple color, which is where it would have been in the middle, when there's similar amounts of H ind and ind minus, and now it's going to turn to a blue color in the acid. Yes, that's what we're going to do now. What would happen, and I guess, Ansh, you volunteered yourself to answer this. In a basic solution, what color would the indicator become and why? Is that your final answer? Apply the same principles, not asking anything crazy here. What did we do? We asked ourselves, what's the stimulus? So you tell me what that is. What is a base release in aqueous solution? Good, right? Now, is hydroxide ions in this equilibrium? No, there's no hydroxide ions. So this solution of the base has hydroxide ions. The hydroxide ions aren't in the equilibrium, so directly there's no impact. But what will the hydroxide ions react with that is in the equilibrium? Yeah, so because we have the base, the OH minus is going to react with the hydrogen ions to form water. And so what is the stimulus going to be for this equilibrium? I want you to be more specific. Good, that's what I want to hear. There's going to be a decrease in the concentration of hydrogen ions. What is the exact opposite of that? Increase in the concentration of hydrogen ions. So, Luca, I want to increase the concentration of hydrogen ions. Would I shift this equilibrium? Would I shift it to the right, or would I shift it to the left?
To the right.
Very good. When you shift to the right, you make more hydrogen ions, you increase its concentration. Perfect. So the answer is we'll shift to the right-hand side. So look at what color would this indicator become now. Since we shift to the right, we make more ind minus, which is what color?
Red, more reddish
Very
color.
good. Exactly. So now in a basic solution, your indicator is going to light up red. It's going to go from purple to red. Do you see how indicators are working now, everyone? The principle here is most indicators are weak acids. Because they're weak, they form an equilibrium. And the second most important thing you have to remember is the ionized and the unionized form of that indicator have two different colors. That's our one. What do I mean when I say the ionized form of the indicator? Not quite. Ionized means it's an ion, which means it has a charge. So this is the ionized form of the indicator. This is the unionized form. So you need to say there's 2 points. First point is most indicators are weak acids. Second point is the unionized. I'll write this down for you to help you out as well. It's also in your notes. But and look, you'll get access to this as well. And you can get it posted, printed and posted to you as well if you need it. Okay?
Okay, thank you.
So the second thing I'll write is the unionized and ionized form of indicator have two different colors. Very good. Make sense to everyone? Good. All right. That's all you need to know about indicators. So now you know how indicators work. You now know how we use them to study acids and bases. They will change color to help you identify acids and bases. Does that make sense to everyone? Have. Sorry. Have is the word. Have two different colors. Good. Happy to move on? Yeah. Why do they have specific colors? So you tell me, what does it mean when my shirt is a dark blue? Or what does that mean to you? So this white light from the ceiling is hitting this shirt. What is it reflecting to your eyes and what is it absorbing? Are you sure it reflects that to you? It reflects blue. It absorbs every other color, right? So the reason you see a dark navy is because it's reflecting navy into your eyes. The fabric of the shirt is actually absorbing every other color of white light, which is the entire rainbow. It's reflecting blue. So the answer to your question is to do with the structure of H end and end minus. They will absorb different wavelengths of light due to their structure and the bonds, and they'll release different wavelengths, and that gives them two different colors, just like how different shirts have two different colors. Okay? Good question. Now, you have to memorize this table. I'm kidding, right? We used to have to in the old syllabus. That's why they've shifted it now. The old syllabus used to be very much memorization and just memory testing. The new syllabus is much more application, which makes it much better. So you don't need to memorize this, but for your trials, especially if you go to a selective school, they definitely can ask this. And I have seen them ask for the indicator ranges as well. So I'd say, even though I was joking, kind of not for most of you. Okay? So for your trials, you should know it. HSC will never ever ask the specific numbers. Okay? I'd say important ones would be these three. The reason these three are very important, everyone, is because we use them in titration. They're very common indicators used in titration. So when I teach you about titration, you'll learn that we know when to stop the reaction between an acid and base based on where the indicator changes color. Okay? So I guess there's not much to say except the way I remember this, a little way to remember it is I remember the rainbow. The rainbow is Roy G. That's the color of the rainbow, right? So methyl orange goes from red to orange, and then finally to yellow, right? And the range is 3.1 to 4.4. Now bromothiamyl blue goes from yellow to blue. So in the middle, what color would it be? Green. Very good. Phenolphthalein is just a weird one. It goes to pink. So to remember. That's it. Make sense? The numbers, you can focus on remembering that later. Don't commit it to memory just yet. Okay? Just get the principles. Here's the pros and cons. It's very intuitive. If you have logic and common sense, you can understand. When you add an indicator, you can't get that indicator back, and you permanently change the sample, right? Because it now has a unique color to it. So you technically call it a destructive test. The other thing is an indicator won't tell you how strong an acid is. It won't tell you if you put your finger in whether it will just bubble or whether it will melt your skin off, right? It will just change color to an acid color or a base color. You won't know how strong the acid or base is. That's a weakness of indicators. But we'll move on. Again, this, you can read that in your own time. I would not even commit that to memory, just additional info. Let's move on to this question. Again, I'm not going to say anything. So the dot point you're learning this is, what are the products of acid-base reactions? And you're going to learn it through this way. So if you paid attention in year 11, you should know how to do this. So I'm going to give you a minute. Luke, I'll get your answer too in a minute, and go through this. So 1 minute. Let's see how we go. Wait, was advanced maths hard for you? I think I asked you this last week, but a lot of students were saying it was a bit more challenging than they expected. Pretty hard?
Oh yeah, it's gonna be easy next year.
Is that what?
I doubt.
I doubt, yeah. There's no trend. Yeah, there's no real trend. Yeah, that's fair enough.
But you know, like the advanced
Is that right? I remember when I was doing my HSC, Greek was my weakest subject. So I kind of crammed it and left it to the very end. And I was so lucky. That's probably the one exam I was a bit stressed about. I ended up, because it was one unit, I ended up getting 48 out of 50, just because they asked the questions which I studied for the day before. So I was very lucky. Otherwise, and it didn't count to my HSC, which is the saddest part. So yeah. Who's doing 11 units? Yes, the one unit that you study is not going to count to your ATAR at all. Just the, only 10 units counts towards your ATAR. So the 11th unit, or whether it be extension 1 or a unit of physics or the weakest subject, just does not even count.
I'm doing extension maths.
Are you doing extension 1 maths? 2 or 1? So yeah, if that's your weakest subject, it won't even count to your HSC. Physics. Then half of your physics marks will count, half of your maths will count. So average it to get you a total. Yeah. All right, so what do we get? What's our answer? So I'm going to just walk around and see how we're going. Left-handed. Wondering why it was hard to get it with you. Give you a study in a sec. Get some water, I'll be right back. And do remind me, class, if we hit the hour mark and I haven't given you a break, feel free to remind me for a break, okay? Because it is very important so you stay focused. Yes.
Just completely ignore them. Can you take photos of like the class and stuff? So maybe never mind. Do one of you guys want to even use? I need to like take photos of the book that I just gave you. So.
Wait, I haven't done this one.
Oh, did you just come? Yeah.
Oh, Betty, you're so smart. That's cool. Yeah. That's it.
Sorry, are you I'll go get one for you now.
After this.
Concentrated. Same thing. Wow.
No, it's a photo.
Is this 2 plus?
So, Austin, what are you currently up to at school?
So we just did the combine.
Then, how come your exam was on acids and bases? Is that your own research? So we're ahead of the school right now.
Yep.
Good. Let's keep it that way. All right. Continuing on, I'll give you a break in about 5 minutes. Okay, we'll just quickly finish upon this concept. So, what was the net ionic equation for now? Na plus Cl minus gives NaCl. Are we sure? Did everyone get this?
Well, the first
I disagree.
The first one I got was hydrochloric acid plus sodium hydroxide gives sodium chloride plus water.
Hydrochloric acid plus sodium chloride gives you. Sorry, not sodium chloride, sodium hydroxide gives you sodium chloride and. Okay, so when you're trying to find the net ionic equation, what do we need to do, everyone? Everything that's aqueous, we break it apart. Now, what is aqueous here? Everything except NaCl is a group 1 metal. It's aqueous. So this is H plus Cl minus plus Na plus hydroxide gives you Na plus Cl minus plus H2O. Now to find the net ionic equation, what must we do? Regard, we need to remove the H2O. The reason it's called a net ionic equation is we're getting rid of the spectators. Regard, who are the spectators here? Who's on the left and the right hand side? Very good. Na is here, Cl is here, and here. Remove it. So we're left with H plus OH minus gives you H2O. That is the actual net ionic equation. Now, what did you all get for the net ionic equation? I'm going to give you one more go to do it for the second reaction. To do it correctly this time. Are you done for today? Okay, good. Yeah, sure. Does anyone have any interesting plans for the coming week?
The holidays, we're going to do a bunch of stuff.
Oh, I'm very excited for that. I've been watching the spoiler breakdown. I'm very certain there's going to be 3.
Right?
Yeah.
You know what I think? I think Andrew Garfield, he's going to come in and he's going to say, MJ.
Yeah, I did see the. Very good. So hopefully you learned concepts from this question, which is every single neutralization, unless the carbonate acid neutralization, has the exact same net ionic equation. Does that make sense to everyone? That is the only conclusion you can make from this. So the second reaction has the exact same net ionic equation. So now you know all neutralizations are H plus OH minus joins water. Okay? Good. Any questions? Good. It's a very important point to note. And I guess the other point I want you all to remember, it's not part of this question, but every single neutralization reaction goes to completion. It doesn't matter if it's a strong or weak acid and base, all neutralization reactions go to completion. Can you write that down? The only exception is when water is involved, but you'll learn about that soon. So it's not an immediate priority as of now. All neutralization reactions go to completion. Very good. Look at any questions. Did you get the same equation for the second reaction as well? Anything you wanted to clarify?
Wait, you just like cancel the things out, right?
Yeah, everything that's aqueous, you want to cancel that out. So what we do is everything that's aqueous, you first split it apart. Do you see how I split it into H plus, Cl minus? And then you cancel out everything that's on the left and the right hand side because that's your spectator ion. It's not actually taking part in the reaction because it's on the left and it's on the right hand side as well.
Okay, thank you.
Good. All right, everyone happy to move on? Okay, now let's just see what the next question is all about. Acid carbonates. Yeah, sure. How about I very quickly spend a minute on this and I'll give you a 5-minute break after this. Okay. Now, this reaction, it actually has a name because it was such a problem for scientists in the early 1900s that they called it the ammonia dilemma. Okay? The reason it was called this is because what you're seeing in front of you right now is a neutralization reaction. This is an acid. Ammonia is a base. This salt is not acidic or basic. It's slightly acidic, you'll find that out soon, but it's not a strong acid or base. It's been neutralized. This strong acid here has been neutralized. That is the key point. But do you see any water? Do you see any hydrogen ions moving around? Do you see any hydroxide ions? So using your current theory of acids and bases, you could not explain this reaction. This is the single reaction that prompted a whole new theory of acids and bases because we could not explain this. And the main issue was, everyone, the states. You'll see that? It's not aqueous, which is why you don't see any hydroxide, you don't see any hydrogen, you don't see any water. And you'll find out how to explain this reaction. All right, moving on. Acids, carbonates, just do not forget CO2. Last lesson, virtually everyone forgot acid, carbonate, salt water, and carbon dioxide. Okay, so maybe underline that if you feel you'll forget it. And I guess the only other thing is acid metal. This is the least high yield. It will virtually not ask you. This is more your level knowledge. But you form salt and hydrogen gas. Okay, good. So M, in these questions, what does M represent? Yeah, good. So nothing else to mention there. Good job. All right, on that note, take a 5-minute break. Stand up, everyone. And Luca, same for you. Stand up, stretch, get some water, and we'll recap in 2:45. Okay? So you're energized when we come back to class.
Okay.
If you have any questions, well, feel free to ask me.
Okay, thank you.
You want water? Yeah, you can go. Try not to wander around though. Yeah, the right side to the front, it's the left.
I have a question. In my system, when you have to do a table, right, it has to be within 2 pages. If I use like an image and then explain the image, would that be good?
I need more context. What is this about? So what's the table about?
We're doing processes in like a international process, and then
So you want to just include flowcharts?
yeah, so then just flowchart and down about the solvent principle. And then it's like color coded. I was thinking of just explaining it with the
Are you doing a video not with file?
just
Flowchart.
so I was going to write down my
You have catalysts and temperatures.
No, it is. Just physics and
You need temperatures.
Math.
So you find which of those reactions are equilibrium and temperatures and pressures. Maybe, do you have a tabulating device or anything of that sort? It's so you can put it in Word, you can get arrows, you can like take temperatures as well. I would just include them in text. I think that'd be good.
So I was thinking of like just creating the image and then coding it according to the others.
Are you going to be marked on that flowchart or on that paper? Or is it
Or like
bringing in exams?
So we get it's 5% weight for the table and then 10% for the legal.
Go ask your kids, the people in your above, what their assessments look like. So ask for a copy of their assessment if they can give it to you. Compare it to yours. I'd say what that's missing is actually catalyst temperature. If you have that in your paper, okay. Keeping this out of the program as an examiner is so you can explain the weight in you.
Yeah, but I think it's part of the
Good. I can send it to me when you're done.
yeah, that's what they do. No, they're going to they're trying to establish this phenomenon, and they're to like actually pass the course. That's what they're doing to like as a what is your I didn't realize it was 8 minutes. It's like it's not like office is like did you buy it?
Otherwise, it goes.
I'm actually lost.
honest, the thing is, I'm coming back now. I'm trying to read other important literature books now because there are some really good books out there. And the books that keep coming up are English prescribed texts, like Brave New World. Pardon? Life of who? Pi, yeah. Is that a prescribed text?
Yeah, well,
Oh, but I read it. It was a good book nonetheless. It was a really good book. I think that's a really interesting book about. I think it's more religion, but you can interpret it how you like. All right, we'll move on now. So this is just. We'll start with the dot point, so you know why we're learning this. So this is the aspect of the module where you need to discuss your industrial and everyday uses. My tip to you is have 2 everyday uses, 2 industrial uses, memorize a one-liner, key important info, move on. Okay? So the syllabus has, your notes have everything here. I guess I'll just quickly touch upon it again. What disease do we treat antacids? What disease do we give antacids for? Heartburn, good, but what would you write in your exam? Esophageal reflux disease. Esophagus, I know, is hard to spell. Sometimes they have an O in front of the E, which confuses you. Just spell it how you'd like. You're not going to lose marks for spelling this right or wrong. But yeah, so gastroesophageal reflux disease. It's characterized by acid, so you can see HCl has about a pH of 2. Does that tell you if it's strong or weak, the pH? pH is all about concentration. Remember that. It has nothing to do with the strength. Okay? Good. So hydrochloric acid, the acid itself is strong, but it's also very concentrated. And what happens is it can travel back up the esophagus. And this is because this region here is what we call a sphincter or a hole, right? It typically is quite closed off and kinked, such that acid can't move back up. But certain people, especially when you're overweight or you get older, the esophagus, it gets a little bit less kinked and then the acid can travel back up. Okay? It typically happens when you have alcohol, spicy food, and it's bad because you can irritate the lining, cause mutated cells that can become cancerous.
So you know how some people have eating disorders, right?
Yep.
And they're like,
Vomit a lot, they increase their risk of, they definitely get esophagitis or inflammation and etc. Yeah, so can you all see how it's kind of kinked off? So this is, do we know what we call this? This is a muscular dome, where when you breathe in, travels down. Yes, your diaphragm. So you can see how the diaphragm kind of kinks the esophagus there. So acid that wants to travel up kind of just moves back down, right? Yeah, your diaphragm's on top. So your esophagus pierces through the diaphragm and then becomes your stomach on the left-hand side. Yeah.
oh wait, so your diaphragm is covering the stomach?
So your diaphragm is the division between your chest cavity and your abdominal cavity. So if we're talking about your abdominal organs, they're all underneath the diaphragm. This is more medicine. Let's focus on the chemistry.
So does the diaphragm push the lungs down?
Your diaphragm is below the lungs. And it's connected to the lungs and the heart. And so when it moves down, the lungs will also inflate. Yes, when you exhale, the diaphragm moves back up. So it relaxes. Yeah. But, good. Anyway, moving on. I guess antacids, just remember they contain metal hydroxides and carbonates. Possibly have one that you remember. So I just remember calcium oxide. You can remember aluminium or zinc hydroxide if you'd like. Okay? Any questions about reflux disease? You don't need to go into the medicine, don't need to talk about sphincters, just mention reflux disease is managed with antacids, which neutralizes the stomach hydrochloric acid. Okay? Good. All right, finally, toothpaste. The key principle here is bacteria consume sugars and they produce acid. And toothpaste contains metal oxides and carbonates that neutralize the acid. Now, the reason that acid is bad is because it literally leaches or dissolves bone, right? And your teeth are bone. So what happens is you can actually leach the crystals, the calcium crystals that make up the non-living component of bone. As you can all understand, bone is hard. It's not just cells. It's cells embedded in non-living calcium material. It makes it all very hard. Okay? So the acid can actually leach or remove that calcium part of the bone and thus dissolve the bone. Okay? So to prevent that decay, we use carbonates in our toothpaste. Good. Here is an interesting reaction. Sodium hydrogen carbonate and tartaric acid. You don't even need to know what tartaric acid is. What product would you produce in this reaction? Good. And the CO2 will fill the dough or the mixture and cause it to raise. That is all baking soda is. If anyone has used baking soda before, it causes things to raise. The reason is it causes a neutralisation reaction, and the CO2 is what causes the entire, whatever you're cooking to raise. Very good. Okay. This is a bit about the body. Does anyone know what bile is? Yeah, so your liver sits about here in the right side of your body. Okay? You can actually, in medicine, we do this thing where we tap. Has anyone gone to the doctor before recently? No? But when you might go to the doctor, they'll tap your chest region. If you go to the emergency department, they can look at the size of your liver from that, just from the sound, the change in sound. Behind the liver is a gallbladder, and the gallbladder stores all the bile. So bile is this green, this like bright green pigmented solution that you release into your intestines to absorb fat. Okay? It's also basic, so it neutralizes any acidic remnants of food from the stomach as well. So I think the key thing here is bile is basic. Good. For industrial applications, I don't remember salt pH. It's boring, that's why. So move on to fertilizers. Fertilizer is exactly what I told you. The ammonia must then further react with the sulfuric acid to form ammonium sulfate. And it's the ammonium sulfate that is used as fertilizer in soil. Okay? Good. Not much else to mention there. I guess, again, fabric dye, you can remember that as well, just so you have two industrial examples. So I guess one thing to note is, label it for you. I want you to highlight these sections. Good. That's the key principles of that dot point. The gist here is a lot of your natural fabrics, like polyester. So polyester is a fabric we can artificially produce, or we can naturally source as well. In fact, if you look at the back of your shirts, the majority of your shirts will have some element of polyester at the back. Okay? So when we're trying to dye polyester a specific color, the natural waxes can prevent it being dyed, and so we add a base to bleach and remove the actual wax. And then we can add acetic acid to neutralize the sodium hydroxide that we add. Okay? So fabrics rich in wax, sodium hydroxide removes the wax to enable easier dyeing. Acetic acid neutralizes any additional sodium hydroxide attached to the fabric. Okay? Good. All right. Let's move on. All right. I want to give you a question. How about we'll do that very shortly. Actually, I'll give you this one right now. Question 1, checkpoint B. So I'm going to give you all about a minute to conceptualize and explain your answer, and then we'll move on from there. Ambient is just outside. Okay, so Prithvi, why do you think that we have this observation? Absorbing the temperature. Can you absorb a temperature? Absorbing heat. Yes, it does.
Is it because there's like a large body of water that it spreads out?
There's a large body of sand.
So we don't know how big it is
Let's say it's a huge body of sand. You need to know the structure. Think about it, this is HSC content, right? You need to know the structure of sand. Other than it's a covalent network substance, nothing else. Thermal conductivity of water. Of water is lower than sand. Do covalent network substances conduct? Do they have free electrons? So both are relatively insulated. Pure water doesn't conduct either. The reason you see, water conducting in movies is because it has ions in it, which enable it to conduct. Pure water does not conduct. Why? Something in water. Come on, we're going into magic here, not chemistry. The answer is letter. I want you all to think before you articulate yourselves. What does this letter mean to you in terms of chemistry? Let me help you out.
Is it the specific heat capacity?
Yes, very good. Good job, Luca. C is this. You've all been saved. That's not the same thing. Specific heat capacity and thermal conductivity are very different things. Okay, that's why you're probably the closest, but you're still very far off. Because water and covalent network substances don't conduct, right? Specific heat capacity isn't to do with conductivity. It's how much energy you need to put in to raise 1 gram of that thing by 1 degree, right? That's very different to just whether it conducts or doesn't conduct, right? So water has a very high specific heat capacity. What that means is you need to input a lot of energy to get even 1 gram of water to raise its temperature by 1 degree Celsius or Kelvin. Remember, Celsius and Kelvin are different starting points, but each incremental increase in 1 degree Celsius is the same as 1 degree Kelvin. It's just that 0 degrees Celsius is how much Kelvin? Good, negative 273.15. Very good. All right, so, okay, so moving on. So specific heat capacity is the energy. Who wants to define it for me? Because I've kind of already given it to you. Good, and what was C? Luca, do you know what C is for water? What the value is for water? So it's in joules.
I don't know, sorry. I don't remember it.
It's a data sheet, so you don't need to know it, but it's 4.18, right? 4.18 joules per gram per Kelvin. You might see in your data sheets 4.18 times 10 to the power of 3 or something like that. That's because they're doing it per kilogram, right? I like to do it per gram. In chemistry, you work with mass in grams. So you don't want to keep converting stuff, okay? So remember this. The answer is, it's because water has a much higher specific heat capacity than your sand. So when you input the same amount of energy to sand and water from the sun, since sand has a smaller specific heat capacity, its temperature will go up much more, whereas waters will not go up much more, because you need much more energy to even raise the temperature of water by 1 degree. Okay, that's your answer. The reason I brought this up was to introduce enthalpy of neutralisation to us. Now, first thing you need to know, what is molar enthalpy of neutralisation? What does molar mean? Per mole. So you know this is some value that's per mole. What is enthalpy also known as? Change in heat or energy. Energy, and mainly in chemistry and HSC, we assume it's all thermal energy. Okay, so we know that molar enthalpy, so we straight away know looking at joules or kilojoules, because enthalpy is typically measured in kilojoules because of the huge energy changes. Kilojoules per mole of something, right? And what reaction are we looking at here? Now you tell me, all of you, what was the one substance that is always common in neutralization? Water. So what do you think we're always going to do it per mole of? Per mole of water. Perfect. Very good. So the molar enthalpy of neutralization is the energy released in the neutralization process per mole of water. So kilojoules of energy released in neutralization per mole of water. Now, who can tell me, is this going to be exothermic or endothermic? So imagine right now that someone just dropped very concentrated sulfuric acid, very concentrated, to the point where it can melt skin. And it's slowly traveling towards all of you, right? You have sodium hydroxide in Rabab's table. You have sodium hydrogen carbonate in Mahi's table. What are you using to neutralize that?
Wait, say it again.
This is your thought experiment. Concentrated sulfuric acid is coming towards you. You have two containers, sodium hydroxide or sodium hydrogen carbonate. What do you use to neutralize this acid spill? They have asked this in the HSC, not as like you are getting melted, but as in there is this chemical spill using neutralization. Explain the rationale for the use of this agent. Yeah, close. So what state would sodium hydroxide typically be in? Aqueous. What state would sodium hydrogen carbonate be in? Solid pellets. So solid pellets would also absorb the actual acid. But there's another reason. What did we say about neutralization? It's not endothermic. What is it? It's highly exothermic. It's in fact one of the most exothermic reactions in chemistry. You must know this. And there is a number I want you all to remember. Negative 57. Typically, a strong acid, strong base, neutralization results in negative 57 kilojoules of energy, aka 57 kilojoules of energy gets released per mole. So if you use sodium hydroxide, which is a strong base, with your sulfuric acid, you would release that much energy. That could melt the floor, depending on how much acid or base we have. Does that make sense? So it become extremely hot. So now you don't have an acidic solution coming at you, you have a boiling solution coming at you. Okay? Whereas if you use sodium hydrogen carbonate, this is a weak base. A weak base does not release as much energy when it neutralizes with an acid, so it'll be less than negative 57. So that is a chemistry rationale as to why, to neutralize an acid spill, we prefer to use a weak base than a strong base. Less energy is released.
How do you know it's weak?
We'll talk about that. I haven't mentioned anything about strength to you yet, but I'll teach you all that later. It's just to do with the compound. You should be able to see it, and from memory be able to tell that it's strong or weak based on the ion. We'll talk about that soon. But very good. But hopefully that makes sense. Neutralization, you're never ever going to say endothermic again. What is it, Anj? Highly exothermic, negative 57 kilojoules per mole. Now, the last thing you'll notice in chemistry is they want to always have a standard reference, right? Because things change with temperature, things change with pressure. So what we want to have is a constant temperature and pressure that we can measure this enthalpy of neutralization by. So the final part of your definition for molar enthalpy of neutralization is energy released per mole of water in neutralization at standard temperature and pressure. You can see here, 298 Kelvin. That's not standard, that's room temperature pressure. Do we know what standard temperature pressure is? It's 0 degrees, right? Yeah, so room temperature pressure is 25 degrees or 298 Kelvin. Very good. Good job. All right, now what are the two equations we need to solve enthalpy of neutralization? Just enthalpy questions. You've done this in year 11. You've done a bit of this in maybe junior chemistry, I'm not sure, but there are two equations. Q equals 2. What's the second equation? Triangle H equals to negative Q on N. These are two very different equations. Now, Pranav, I believe I've explained this to you before. Q equals to MCAT is solely to do with what? Yes, of what substance? Water, right? So Q is solely to do with water. I'm not talking about water and neutralization, everyone. I'm talking about the volume of water that changes temperature. Now, pay attention to this. Do you all realize the majority of your neutralization reactions, or any calorimetry experiment, do you all remember you used a styrofoam cup? You might have used 2 styrofoam cups, and you would have measured the temperature change of water using a thermometer here. Does everyone see that? Now, is anyone completely confused? Never seen this before in their life? Never seen this before? Never seen this before? Never seen this before? Never seen? Okay, I'll explain this to you. Okay, so this is what we call a calorimeter. It is an instrument that measures energy. Measures energy changes in a chemical reaction. And a calorimeter is used in calorimetry. What does metry mean? Yeah, the measure of something. What does calor mean? It reminds you of calorie, which is a unit of energy. So calorimetry is measuring energy. And what instrument do you use to measure energy? Calorimeter. How easy is that? Not too crazy, right? Now, the way we measure energy changes is we measure how a reaction changes the temperature of a mass of water. Okay? So what we're going to do is we will add reagents, substance A and substance B, to this water. Everyone with me? They will react. And if they're exothermic, Prabhat, do they release energy or do they absorb energy? Yeah, exo. Release or absorb? Think about this. It's an exothermic reaction. It's like an explosion. It's going to release energy, right? So think about this. A and B get added to this solution of water. They're going to release heat energy. What's going to happen to the temperature of water? It's going to increase. So your thermometer is going to measure a temperature value or a final temperature that increases. Does that make sense? So the change in temperature will be positive. Everyone with me? Okay? Now what you're going to do is you're going to apply these 2 formulas. Q equals to MCAT will be your first formula. This is solely to do with the water in that vessel. Q represents the energy that water has absorbed. That's what Q is. Energy water has absorbed. And it's typically you calculate it in joules. Okay? What would M be? Yeah, the mass of water. Mass of water. It's the mass of water in this calorimeter. So you would have pre-weighed, let's say, 200 grams of water. So what would you sub in for M? 200. That's it. What would you sub in for C? 4.18. Why? Because we're using water, which has that high specific heat capacity we just spoke about. Do we have temperature? How did we measure temperature? Yeah, we just use a thermometer, final minus initial. The lowest temperature, highest temperature. Subtract the 2. Very good. So what can we find now? Q. And let's say we used exactly 1 mole of A and B. Well, let's say we just use 1 mole of A for the reaction. What can we do? We can go, okay, well, the energy change for this reaction is Q joules of energy per 1 mole of A. Now you know the enthalpy change or the energy change for the reaction between A and B. Is everyone with me? Did you see how we use temperature change to measure the enthalpy for a reaction? That's exactly what we're going to do here. Now, pay attention. In neutralization, what did we say this N value was? Per mole of? So only for neutralization, it's per mole of water. Now tell me this. If this is 200 grams of water in this vessel, and from the neutralization, because you know how in neutralization H plus reacts with OH to form, let's say from this reaction I make 0.001 grams of water. What mass of water am I subbing in for to find this N? 200 grams or the 0.001 grams? 0.001, right? Remember this, the Q has everything to do with the entire vessel of water, the N has to do with what we made in the reaction itself. This is a rare time where the reaction makes water as well. So that's why it might be a little bit confusing. So which water do we use? You have to use the water that was made in the chemical reaction of neutralization, not the water that was always sitting in the calorimeter. Does that make sense to all of us? That is the biggest silly mistake I've seen students make for these questions. Now, the best way for you to do these questions is to start doing them. Jump right in. So I'm going to throw you on the deep end and give you a question. Here you go. This is an example exam question you would get. So again, I'm going to give you all about 2-3 minutes to solidly work on this. Same for you, Luca. 2-3 minutes, and then I want you to message or me the exact answer you get, or I'll ask you to read it out for me. And if you're not sure, that's completely fine. You can jump in any
Okay.
step, call out and just say.
Okay.
Specific questions. Okay, so 2 minutes. Let's get through this. Okay. I'll leave it to you guys. Get some water. Recap in about 2 minutes. Feel free to discuss among each other if you have any questions, but follow the exact same steps you've always been following for calculation questions. What is the first step? Good. Raval, what is the second step? Good. What's the third step? Tanisha? Diagram. If you're stuck, go to diagram. If you're still stuck, no, what do you do? Yeah, you frame the question. You ask, well, mathematically, what is it I'm trying to find? Is it N of NaCl? Is it C of HBr? What is it I'm trying to find? And if you're still stuck, Maya, what should you do? Find moles. That's it. You follow, I'm telling you, follow those same steps. You will never miss a chemistry calculation question. If you can perfect those steps, chemistry is very easy. Chemistry is literally just following those steps, regardless of how complex the question is. So good luck. There's only one thing I will say though, is be cautious of your units. What unit was Q? What unit is H? So be cautious of that when you're changing between the two. Okay. Good.
But how do we find out N if we have equal to us two constant? Do we add the one? Then we. Well, I think it's the same way. Yeah. But we're not going to. Yeah, I'm just at it. Wait, that's supposed to the game now. Oh, yeah, because. Yeah. But I don't think I'm going to go away from No, it's killing. Yes, we have delta thing. We need N and T. This so we need to find the N of the equation. Yes, two substances go that way. Just add it. Oh yeah, what do you just add it? Okay, yeah.
So 0.1 times press
Wait, can't you has anyone learned Oh, no, I'm not using that.
Yeah, it's a good point.
Where's that doing one question? What did we just equal? Take it, is it? Oh, is it? I found it. You know what? I didn't find it. Oh, really? There's no one. Yeah, I found it on my day. But oh, that was asking. Yes. Any other idea?
You have to find the moles.
We figured that out.
Yeah, and then you have to go to the.
Okay, let's make it diagram. Guys, diagram. I'm getting two different walls. I don't know which one to use.
We're going to do the reagents. So you
How do you know?
because it's left.
Okay, 7, 9, 9.
Yeah, 2009.
Okay, we use it.
Yeah.
Okay, is that it? That's it.
Who's got an answer?
Wait, still wait.
Anyone finish?
We have concentration and volume. 110.
Why, you guys, do you feel like you're missing data or?
I just insist.
Okay, I think throw you on the deep end. This question wasn't even asking for enthalpy, it asked you to kind of work backwards, right? Which is what makes it a bit more challenging. But nonetheless, you should be able to do this question. Okay, so let's do this together. Maher, what's the first thing I do? Good, right? Equation's easy. So, what is the equation we have, Maher?
HCl
Yep.
KOH
Yep.
equals KCl increase
Yes.
plus H2O.
Good. Balanced or unbalanced? Good. Yes, it is. Good job. All right. Now, Pranav, give me my data, and I want this all in mathematical format. Okay, good. So we'll write that kind of separate because that's its own thing. So delta H equals to? Good. Just by kilojoules per mole. What else do we have? Okay, so we're going to write V of KOH equals to? Good. Times? Good. Always convert it straight to the correct units. Good. What else do we have? It's a C of KOH. I want you to give it to me mathematically. Equals to? Good.
We have 0
Good. V of HCl is? Good. What else do we have? Yep, I've got 1 moles. Yep, good. Good. Now, do you all agree that's also separate to the reaction, right? Ti is more to do with the volume of water in which this reaction has occurred. So we're just going to write, I'm going to do a little bucket of water here. Ti is equal to? Ti is 25 degrees. No, not needed, because remember the change in temperature is what we care about, and it's constant in Celsius and Kelvin. Tf is, we don't know. We want to find that, so that's framing the question. So we need to find change in temperature. Everyone agree? Good. Okay, so what do you all notice now? So I've done my diagram. What's the volume of water that I have in this calorimeter? I've added some of my HCl. I've added some NaOH. What's the total volume? Sorry, KOH. It's 27.9 plus 31.25. Does everyone agree? That's the volume of water here. So we're going to write volume of solution equals to 55.15? Okay, 59.15. Good. Times 10 power negative 3 liters. What do you want to convert that to? Yeah, mass, right? This is virtually all water, right? In chemistry in E12, you can imagine that when you add salt to water, the salt does not take up any volume. You just imagine it completely dissolves in the water. The volume of water is the volume of the solution itself. So you can now say, since water has a fixed density, to the mass is also going to be 59.15 grams. Is everyone with me? Good. Do I know Q? Do I know Q?
Yeah, that's something negative 57.
Is that Q? That's delta H. So we still need to find Q. Okay? Yeah, you can find Q, but we don't currently have it. Does everyone agree? Now, let's go back to this equation. What I said. We've done equation data, we've done diagrams, we framed the question. If you're still stuck, what do? Find moles. Now look here, you've got a C and a V. What can I do? Find N. Now, everyone tell me this. When we have different moles of both reactants, what kind of reaction is this? Limiting excess reagent. And do you agree that limiting reagent is going to limit the amount of water that is formed? So the goal is to find the limiting reagent and use that to find the number of moles of water. Then we get an N. Yeah? We've got a triangle H, we've got an N, we can find a Q. And we can work our way there to find T. So again, as I'm saying, we'll go through it. So what number of moles of HCl is equal to CV, which is equal to what?
Wait, what?
Sorry, 3.44.
3.44 times 10 power negative 3. Okay. 3. Okay, moles. Let's store this as A. Let's store this as B. Okay. Luca, do you know how to store in your calculator? Does anyone not know how to store?
I know how to store.
Okay, good. Yeah. So shift store and store it as a letter, and make sure you show that you're working out. So have a look at my working out. It's very step-by-step logical, and that helps the marker follow your working as well. Good. All right. So we've got number of moles of HCl. We've got number of moles of KOH. What do we do next? What should you do? Remember, we need to compare 1 part versus 1 part in our cooking recipe, right? If we were to compare, let's say we needed 2 parts of milk and 1 part of eggs, but we had 1 milk and 1 egg. Who's the limiting reagent? Who's the limiting reagent? I'd say the milk is, because we need 2 parts of milk. So for every 1 egg, we need 2 cartons of milk. If we only have 1 carton of milk, it's the limiting reagent. In the same way, we need to find what 1 part in our cooking recipe is, right? So what I like to do is I divide each mole value by the number in front of that element in the stoichiometric ratio. In this case, it's 1, but I'm just showing you what I would do otherwise, okay? And that will help you find what the limiting reagent is. Good. So in our case here, we don't have to do much else because they're both 1. So who's the limiting reagent? Good. Therefore, KOH is a limiting reagent. Is the limiting reagent. Remember, the reason it's called the limiting reagent is because it limits the amount of product we produce. What's the product we care about? Water. So we're going to find the number of moles of water. This is where we do what I call applying the stoichiometric ratio. This is where you write whatever you want. So you want the number of moles of water. Does everyone agree? We're going to equate that to the number in front of itself in the stoichiometric ratio. What number is in front of itself? There's a 1 in front of water, so we're going to put a 1 there. What number is in front of the limiting reagent, which is the other substance? 1. I'm just going to put that and then write number of moles of KOH. And that makes sense. For every 1 mole of KOH, there's 1 mole of water produced. Right? Good. So then we can say number of moles of water is also equal to B. Now, triangle H equals negative Q on N. Does everyone agree? That was the equation, right? We've got N. Remember, N was always the water that was produced. Do you see how we're not using the 59.15? We're using the moles of water that was made from the reaction itself. So that's the big important point to stress here. Can I find Q? Q is negative triangle H times N. So that's equal to negative of negative 57.2 kilojoules per mole times B moles. What do we get? Yeah. Okay, and that's kilojoules, right? Good, 159.59. Yep, joules. We'll store that as C. Has everyone got in that? Okay. Now the final step. Do it here. We've got our Q value. Q equals MCAT. What do I need to find, Rabab? I need to find TF, and I said for that I need to find triangle T. So let's make that our subject. So what is triangle T equal to? Q divided by? Yeah, very good. We know Q is equal to C. We know N is equal to 59.15. That's a massive solution we calculated. And what's C? Remember, this is the C, which is the specific heat capacity C, not what we stored as C. So 4.18. What's our answer? What's our answer for T, change in T? What do we get? Luca, any questions so far? Does this make sense? I know this is a very, very challenging calculation question.
It makes sense. Thanks.
0.65? Okay, 645. All right. So our change in temperature is 0.645 degrees Celsius. So what do we need to find here? Are we at our answer? So remember, change in T equals to TF minus TI. So TF is equal to change in T plus. So we're going to add 0.645 to 25 degrees, which means TF is just 25.45. How many sig figs? Remember, you always want to have your answer for the lowest number of sig figs as a question. How many sig figs is 0.1? 2? One, two. The answer is 1. 0.1 is 1 sig fig. The 0 in front of that's not significant. So round that off to 30 degrees. As long as you have this full answer, you also save yourself, right? So you round it off to 30 degrees Celsius and you write 1 sig fig. Very good. So that's your final temperature. Does that make sense to everyone? We did a harder version of your question. This is what your trials would ask you typically. Okay? So you all just did a trial level question there. Did that make sense? Now, don't worry, the rest, see, all these questions are for you to do at homework, and I really want you to do these questions before coming in next lesson. Circle this for me. I expect next week, question 5, question 6, question 7 is a very good one. Question 7, you're finding C, specific heat capacity itself. And good. Luca, this week you won't have any questions. Next week you will. So I don't want to start pushing you straight into exam questions, but you get access to all of this next week.
Okay.
It was page 20. Question 4, question 5, question 6, and 7. 4's already been done, so 5, 6, and 7 are the 3 ones I want you to do yourself. Okay? Yeah? Yeah, so you should all have it on the edX website. Yeah. If you go to the edX website, you should have the. Do you have access to it? Ansh, do you have access to the mod 6 booklet? Go check on the edX website. Okay, good. You should all have access. And you're going to get a printed copy next week. It'll be binded to you. Now, next week I may not be taking you guys. There may be a substitute because I think I won't be available then. But if that's the case, that mentor taking you will check your work. Okay? Good. Do we have any questions, any assessments that you're all quite confident? Yeah, send me yours. And the rest of you, all fine and can? Oh, that's good. Okay, well, good. So what you all need to focus on, by your holidays, I want you all to make sure that you finished 5 and 6, right? You want to finish half of year 12 and start smashing through trial papers. You realize in the jump from year 11, so technically also just year 11, term 4, right? To start of next year, there'll be a huge jump in certain students' abilities. You can really differentiate yourself and the rest of your cohort based on the work you do these holidays. So stay consistent, follow a routine, and you got this. All right, Luca, that concludes today. Do you have any questions at all in particular?
No, I'm all good. Thank you.
Okay, and Luca, what school do you go to?
Clancy Catholic College, West Oxton.
Okay, good. And how are you finding chem? Is it one of your easier subjects or harder subjects?
Chemistry's all right. It's just one of my middle.
Okay, and what ATAR are you planning on based on the course that you want to do at uni?
I haven't looked into the courses yet, but I want to go into medicine, so I assume somewhere high, a high ATAR.
Medicine would mean over 99, so it means you need to clear a high band 6 for chemistry. I can definitely help you with. All right, see you guys. Take care. All the best. See you, Tyler. Questions? Just give me 1 second. I'll just finish that up. Okay, good. So yeah, if you have any questions at all, Luca, since you have Teams, you can message me. I'll help you out with the school tasks you have at all. Are you sure? Any questions at all that you might have that you want to clarify from today?
No, I'm all good. Thank you, though.
All right. Well, good job, because you understood everything. You got that specific heat capacity well, which is very good. For medicine, just make sure that you stay on top of your ranks at school. So you want to get rank 1, especially at the school you're going to secure an ATAR over 99.
Okay.
So the ATAR goal purpose of ATAR is to get in a gold course. It's not for any other reason apart from that. And for medicine, I guess you will need to get that ATAR, otherwise you will have to do postgrad, which is a longer pathway and it's tougher as well. Okay, well, I'll leave you to it. Have a good week, and I will see you next week.
Bye, see you.
See ya, take care.